Hello. In this video, we will acquire some comfort with ray diagrams. Here on the left, you see a tree that is scattering sunlight. The sunlight rays are denoted by the blue arrows. A long distance away from the tree itself, the scattered light is parallel. The rays of light are parallel with respect to one another far away from the tree. These rays of light enter a convex or converging lens, and as the name suggests, it causes the rays of light to refract or bend towards the focus of the lens. And in this picture here, I have a screen located at the focus of a lens, and we see the result of what happens when the rays of light converge together or intersect one another. We see an image, and in this case, we see the image of the tree on the left-hand side. And the image with respect to the object is upside down with left-right interchanged. In other words, the image is inverted. We say that this image is real because the image can be put on a screen. When the image cannot be put on a screen, we call it virtual. An example of a virtual image is when you look inside a magnifying glass, you see large, maybe print, if for example you're trying to read small print. And that image that you see inside the magnifying glass, it cannot be put on a screen, unlike in this situation. I'd like for us to be able to make measurements in regards to ray diagrams, and that requires that we measure distances. For example, the object distance with respect to the lens, and also the image distance with respect to the lens. But before we do this, we have to have an agreement about what exactly is a centimeter. And I say here that the width of one cube is 1 centimeter. The width of one cube is 1 centimeter. Here on my graph paper, there are 24 cubes running from left to right. So overall, there's 24 centimeters from left to right here, on which I can draw a ray diagram. In this illustration, we have a converging or convex lens. The object is denoted by an arrow, and we get a real inverted image here on the right side on a screen. So what's the technique for creating images? Well, we first start with a parallel ray. By parallel ray, I mean that the ray of light is parallel with respect to the horizontal axis. This parallel ray of light enters the convex lens, and at the middle of the lens we say that it refracts or bends, and so then we get this portion. And notice that the parallel ray, after it bends, it must go through the focus of the lens. So this is in concert with what we just said beforehand. Remember, we said beforehand that when we have parallel rays of light, they have to go through the focus. Hence the name converging lens. And so again, to iterate, the parallel ray of light refracts at the middle of the lens and it passes through the focus of the lens. Secondly, we have another ray here in green. I call it number 2, and it's very easy to draw. We just draw a straight line from the object through the center of the lens onwards. In other words, it is not refracted. The intersection of those two rays of light gives you the location of the real inverted image. And again, I call it real because it can be put on a screen. In regards to measurements, arbitrarily, I've chosen the focus to be at 5 centimeters from the middle of the lens, and I've chosen the object to be 9 centimeters from the lens. You have to be careful here. How do I count 9 centimeters? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So notice I counted from where? Here, the center line. Also, let's count for the focus. 1, 2, 3, 4, 5. So that's correct. And then let's count for the image. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and about a quarter here. So hence the image distance is about 11 and a quarter centimeters to the right of the lens. And a very fine point, in regards to drawing the rays, I said that the top ray, the parallel ray, refracts at the center of the lens. In actuality, it doesn't do that. It starts to refract right at the beginning, but to help in regards to finding the location of the image, it helps to assume that the refraction occurs at the center. The assumption is that we're working with very thin lenses. To iterate the ray drawing procedure, we first draw a parallel ray, and it goes to the middle of the lens and then refracts through the focus. So that's this one, parallel ray refracts through the focus. And then we draw a second ray, and this ray goes through the center of the lens without being refracted. And here it is. I'll give you a problem later, and I want you to use a ruler to make sure you draw straight lines. In other words, don't give a sketch. We want a drawing. Otherwise, one gets incorrect image distances. Next, I want to give you a definition called magnification. And the definition reads as such: M, the magnification, is defined as a ratio of the image distance to the object distance. The image distance to the object distance, with a factor of -1 in front. And given our above example, we plug in our numbers. 11.25 centimeters was the image distance, 9 centimeters was the object distance, and we get that the magnification is negative 1.25. So the image distance is about 25% larger than the object. The image is about 25% larger than the object. The purpose of the minus sign is to tell us that the image is inverted. That is, top and bottom have been interchanged and left and right have been interchanged. In cases when you get magnification as positive, it would mean that the image is upright. The image is upright. An example of that would be looking into a magnifying glass, seeing, for example, enlarged print. And that enlarged print that you see is upright. Here's the problem that I want you to tackle. I want you to suppose that the object distance is 3 1/3 centimeters and that the focus is 5 centimeters. So notice here that the object is between the focus and the lens. The object is between the focus and the lens. Whereas in our illustration earlier, our object was outside of the focus. But again, for your problem, you're going to put the object here. In other words, this would be using the convex lens as a magnifying glass. And so the reason why you can see enlarged print with the help of a magnifying glass is because you're holding the printed material within the focus of the lens. The letter F, as is obvious, is the focus. And notice that it's on both sides of the lens. The focus is on both sides of the lens. Now, you might say, well, what's the point of having the left focus? Well, we could have used it if we wanted to. So we could have drawn a redundant ray to help us get our final image. And I'll do that now. So earlier I taught you about drawing rays 1 and 2 when the object is outside the focus. And now I give you a redundant ray, ray number 3, and it has made use of that first focus. So you can see that when it comes to ray diagrams, the foci, or focuses, are involved somehow, some way. And again, your problem is given here, the object distance and the focus. And you're asked to draw ray diagrams. You'll draw it for both a convex and a concave lens. In the first case of a convex lens, essentially, I'm asking you to draw a ray diagram for a magnifying glass. And the second part, in regards to a concave lens, what you'll notice is that if you review your notes, that the rays will diverge from the optical axis. Unlike with a convex lens, the rays, if they're parallel, pass through the focus. And then also, I want you to find the image distance and the magnification for both lenses. And here are some notes in regards to virtual images. By definition, a virtual image cannot be seen on a screen. And by definition, a real image can be seen on a screen. An example of a virtual image, again, is looking at maybe enlarged print with the help of a magnifying glass. A couple of more properties of virtual images. Is that the image distance for a virtual image is negative. The image distance for a virtual image is negative. The negative number just means that the image is located on the same side as the object. And so that makes sense. If you have a magnifying glass and say you're holding it above some printed material so you can read enlarged print, obviously the image that you're seeing is on the same side as the object. And in that case, you speak of the object distance as being positive, but you say the image distance is negative because it's virtual. And then finally, the magnification is simply, as we said earlier, defined as negative image distance over object distance. And since image distance is negative, then the magnification is positive. That is, it's an upright image. Make sure you review the notes for diverging or concave lens, and also review the notes for a converging or convex lens before beginning. And that's a wrap.